Welcome to this week's research seminar. Today's speaker is Shizhang Li, and he's going to speak on H star BG.
Thanks. Yeah, thanks for inviting me. Thanks for coming. Right. So I want to describe some joint work with Dmitry, Kubrak here, and Shubhodip Mondal, who will be here next semester. So if you don't understand something I said, you know who to ask. So we have, I think we have understood something, but nothing. Okay, no detail has been written down, so therefore don't fully trust me. But let me describe. Okay, so let's start with some background or maybe motivation. Right. So I guess in algebraic topology, right? So if you have a group or maybe a topological group, then you can form a certain topological space called a classifying space. Usually denoted by BG, and this space will have the following property, which is that given a nice topological space X, then the set of the isomorphism class of principal G bundles on X, okay, up to isomorphism. This is the same. This will be the same as homotopy class of maps from continuous maps from X to this particular space of BG. It's very handy. Okay, so this way, suppose you believe the existence of this guy, then given some principal G bundle, right? Then you will produce a map from X to BG, and then you will get, say, singular cohomology of BG mapping to singular cohomology of X. And this is, I guess, this will be called kind of characteristic classes of this principal G bundle, right? And I guess similar process can be done in the realm of algebraic geometry. Okay, but before saying this, let me say an example, which is that let's say G is S1, then one of these classified spaces can be given by this CP infinity. Okay. Let me write it like this. And then we know that, say, singular cohomology of CP infinity is nothing but this polynomial, polynomial ring with Z coefficient, and the generator is this first term class of line bundle, right? And we can do the same thing in algebraic geometry. So now let's say you have G over S, which is a finitely presented flat group scheme. Then you can form this smooth algebraic stack, also called BG. Okay, so this is a smooth arcing stack. So, the natural question would be to understand cohomology of BG. Your favorite cohomology theory. Right. So let me write it here. The question that maybe you want to understand is what's R gamma BG? Yeah. And I deliberately didn't say what the cohomology theory is, because I think people in this seminar, the audience might be interested in various kinds of cohomology theory and how they interact with each other. So, right. But let me tell you, right. I think only a few years before, there were already several results that were quite inspiring for our project. So previously, so in the setting of the following, so your G could be a reductive group over a field. And the cohomology theory could be either the Rham or a Hodge or Etal. So let me not describe exactly what they did, but let me just say Totaro wrote a paper in this setting, and then Dmitry, Kubrak together with Adam wrote actually two papers in this setting. Okay, and then you can also let G to be slightly different. So say finite commutative group scheme of order some p power and over some perfect field of characters p. And your cohomology theory could be the Rham or Hodge or crystalline. All right, I will later on immediately describe to you some particular result. But so previously, a few years ago, there was a paper by Dieudonné, Bud, and Akil Matthew, describing some. Okay, they did a lot of things. In particular, they calculated the Rham or Hodge cohomology for certain for some BG, and then it's also a work by Shubhodip Mondal calculating crystalline cohomology in this setting. Okay, part of crystalline cohomology in this setting. So now let me. So let me describe part of computations that was made by both Totaro and ABM paper, which actually inspired the talk today. So in Totaro's paper, well, in both Totaro's paper and this ABM paper, they describe to you the meaning of Hodge to the Rham spatial sequence. So there is again a spatial sequence coming from starting from Hodge cohomology converging to the Rham cohomology once you interpret the differential forms on BG correctly. Okay, so let me say Hodge to the Rham spatial sequence for BG is one of the things that interests us. So for now, let me fix K, which is a perfect field of characters P. Then in this setting, okay, so over this field, essentially there are only three finite commutative group schemes of order P. Now I want to describe to you the Rham and Hodge cohomology and their Hodge to the Rham spatial sequence. So first of all, the following is quite, I guess I should say it's well known, right? That if you calculate Hodge cohomology of B of Z mod P, okay, so Z mod P is finite tau, finite tau over K, therefore B of Z mod P, whatever, no matter how you interpret its differential forms, they should all be zero other than, okay, except for the structure sheaf. So then, and then structure sheaf cohomology is just the same as group cohomology. Therefore, it's well known that the result is given by the following. So if the prime is not 2, you will just get a polynomial generator in degree 2, and I guess alpha in degree 1 whose square is 0. But when the prime is 2, you will get a degree 1 polynomial generator. So alpha is in H1, H10, and then beta is in H20. Okay. All right. And from this description, you can also very easily see for just because of the shape of this starting page that Hodge the Rham for this B of Z mod P must degenerate. So the Rham cohomology looks the same. Okay. So I guess this part is easy. And then in Totaro's paper, you can find the following. You can find the calculation of Hodge cohomology of B mu P. So what he did was the following calculation. You can look at Hodge cohomology of B mu P. So this is given by regardless of the prime, it's given by polynomial generator C1 in degree 2 and kind of a degree 1 element whose square is always 0. So this C1 is in H1 omega 1, and then this B1 is in H0 omega 1. You need a little bit argument, but also it's not too difficult to see that this Hodge the Rham spectral sequence for B mu P also degenerates. So and then you get the same description of the Rham cohomology of B mu P. And also write down and then in this ABM paper, they calculated first of all the Hodge cohomology for B alpha P, which is more pathological than these other two group schemes in Curtis P. So here, it turns out that this cohomology, the description depends on the prime. So it's given by, I think I'm following their notation. So when P is not 2, when the prime is not 2, this Hodge cohomology, again, as an algebra, has degree 2 polynomial generators, which they call beta and U. And then there is degree 1 classes alpha and S, just satisfying the condition that alpha square and S square are 0, and then they are anti-commutative. But when P is 2, you will get the following description. So just that this beta becomes alpha squared. And alpha is in H10, beta is in H20, S is in H0 omega 1, and U is in H1 omega 1. Okay. not only did they make this calculation, but they also show that there is only one non-zero. There is only one non-zero Hodge the Rham differential, which is that just on the first page, D1 will send this class alpha to this class U. And once you know this is true, then after taking this into consideration, you will see that afterwards there are no room for non-zero Hodge to the Rham differential. And therefore, do some work, and then you will see that this de Rham cohomology is again given by kind of K beta alpha. Oh, sorry, what am I saying? Beta S. All right, so beta is a degree 2 generator and S is a degree 1 element, and S squared is always 0. So although there is a distinction of the Hodge cohomology ring, depending on whether P is 2 or not, after going through this special sequence, the result is independent of the prime. All right, so is there any question? Okay, now I've described to you 3 data points. I fixed the prime, so I've described to you 3 data points. And if we were engineers, it would be enough to prove the following theorem. Okay, so now let G be a finite commutative group scheme of P power order over perfect field K of characters P. Then we have obtained the following results. So first of all, you can just look at the de Rham cohomology. You can first calculate the de Rham cohomology without going through this Hodge to de Rham spectral sequence, and the result is the following. So first, it depends. Actually, it depends on the prime. So if P is not 2, what you get is exterior algebra degree 1 given by the P torsion of the Dieudonné module. Tensor symmetry algebra given by the Dieudonné module of G mod P put in degree 2. So this is in degree 1 and this is in degree 2. And when the prime is 2, then the description is slightly different. So what you have is you take this, you take the 2 torsion of the Dieudonné module, direct sum Dieudonné module mod 2. So again, this is in degree 1, this is in degree 2. Quotient out the following relation. Okay, so this is for P being 2. And the relation is described by saying that the squaring map. Okay, so the difference between prime being 2 or not is just that if you have an odd degree class, its square need not be 0 when P is 2. So if I take square of a class of a degree 1 class, I will just get a degree 2 class potentially non-zero. And we're describing this squaring map actually. So taking square, first of all, it will land in this DG mod 2. And this map is given by, so let's see. The Dieudonné module is a contravariant equivalence. So DG mod 2 is really D of 2 torsion in G. And then 2 torsion in DG is really D of G mod 2. And then this is a Frobenius linear map. So when I think about what map it could be, well, it has to be the following. All right. So this is the first part, and we're saying that this is the only relation describing this de Rham cohomology. Right. Secondly, we also look at Hodge cohomology, and here's some weird thing. So first of all, if you look at the global forms on BG, it turns out that this is just exterior algebra of global one forms on BG. Okay, and they are all closed. They are all closed forms. They are also never going to be the image of Hodge to de Rham's differential. Yeah, they are never going to be the image of differential under Hodge to de Rham's spatial sequence. Lastly, we also found out that this Hodge to de Rham's spatial sequence for BG always degenerates on second page. So on E2, right? Because, okay, so this, I said E1 degeneration, and this one, I told you that after this, you will get E2 degeneration. So they all checks out the theorem there. And right. And lastly, we have the third part, which concerns a criteria for when the Hodge to de Rham spatial sequence for BG will just degenerate on the first page. Turns out that the following several conditions are equivalent to each other. So first is so G lifts to W2K as a group scheme. And the second part is the same condition, but here you say commutative group scheme. Third condition and the fourth condition are kind of due to each other. So the third condition says that the P torsion of G, which is a P torsion finite flat commutative group scheme, and the condition says that this is a BP1. So I will define this term later. But okay, if you have been to Akil's talk in Princeton, then you know what this means. But the fourth condition is due to this one. So right, it says that maybe G mod P will be a BP1, and then the fifth condition is just that this Hodge to de Rham spatial sequence for BG degenerates in the first page. So it's in E1. All right. So this is the first main theorem. Please ask question.
I mean, are you going to say more about some examples, like how hard is 1 equivalent to 2, for example?
Thank you. It's not entirely trivial. Right. I can. Maybe I will first. I want to first kind of convince you that first of all, this will be related to this by the following remark. Right, sorry. I think this board is getting heavier.
Probably need some lubrication.
Right. So here's a remark. And in this remark, presumably this remark will also explain why we kind of care about whether BG has degenerate or not Hodge to the Rham spatial sequence. So that's a remark. So recall in this in a famous paper by Dieudonné and Luzi, they show that if you have an X over K, which is a smooth proper scheme, sorry, smooth proper variety, then there is the following implication. So X can be lifted to the second vector. So like if your X, if K was FP, then you're asking whether X can be lifted to Z mod P squared. Then this will imply that the Hodge to the Rham spatial sequence for X, well, it sort of degenerates in a range. In the following range from 0 to K P minus 1, suitably interpreted, right? So in particular here, what we are saying is that, okay, so I guess our BG is not quite smooth proper variety, but there are several results. Basic says that you can first of all you will be able to extend this result to sort of general smooth proper arcing stacks, and then if you can find some BG which is liftable, and say Hodge to the Rham doesn't degenerate for BG, then you will also be able to cook up some X which is liftable but doesn't have degeneration for the Hodge to the Rham spatial sequence. Okay, so this is and then I'm not sure if I think I heard this question from Varga whether one could just have a kind of a BG which lifts to W2 but doesn't have Hodge to the Rham spatial sequence degenerate for a commutative G or something. Okay.
You know, maybe you should mention it's not such an example. Like very
Right. So yes. So So this statement is just saying that one cannot find a commutative finite flat group scheme G which does the job, fortunately or unfortunately. Right. But then back to Karen's question. So now if you wanna right. So the reason why we care about this is that this first condition is actually more or less equivalent to BG lifts to W2K. And then the second condition is actually equivalent to, so if your G is a commutative group scheme, then not only can you form its classified stack, but you can also form its higher classified stack. So it turns out that this condition is equivalent to B squared G lifts to W2K. All right. So right. So the logic when we are proving this is basically saying that the Hodge to the Rham spatial sequence for BG is very understandable, so that when this degenerates, then you can also show that similar thing happens for B squared G. Namely, in some low range, the Hodge to the Rham spatial sequence for B squared G also degenerates, and turns out that the differential forms on or the cotangent complex for BG or B squared G are simple enough that this kind of description already tells you that B squared G can be lifted to W2K. I'm sorry, I'm very not very detailed.
But so in particular, your proof of one implies two goes through the cohomological method.
Yes, yes, right. Yeah. And right, and one could ask a general question whether this equivalence of 1 and 2 holds for more general base, other than just the field thickening to W2K. It might be the case, but I'm being recorded, so let me say I don't know. Okay, right. Please ask more questions.
Wait, do you have a version in crystalline cohomology of this?
Oh yeah, that's my next section.
Okay, great.
Right, thank you.
So Shizhang, is there an analogous statement for the conjugate spectral sequence? That is also
Yes.
P3 or
Yes. Oh well. Yes.
P3?
Right. Yes. You just yes. There is also a version for this when you instead of say Hodge to the Rham, you say conjugate spectral sequence. Then this always degenerates on the third page, and then in this equivalence condition you can add 4. Right. Okay. Right. So the next part. Right, as I said, not only are we interested in Hodge or the Rham cohomology, maybe we're also interested in this canonical deformation of the Rham cohomology, which is called crystalline cohomology. So, crystalline cohomology, BG. So before telling you our result, maybe I should first say that in Shubhodip Mondal's thesis, he made the following calculation. So let G over K be as above. Or then he calculates the first few crystalline cohomology of BG. Now this is some WK module. So if you do H1, it will just be 0. And if you do H2, crystalline G over WK, then this is the Dieudonné module of G.
G is plus before.
Yes, G is again commutative. Yes. And this is as WK together with Frobenius. So this description is also Frobenius equivariant, but not for the vegetable. Right. So you can see that this theorem is actually compatible with our description of the Rham cohomology here for the following reason. So let me erase here. So as a remark, so that theorem is compatible with our other description. So this is compatible with guess what? Okay, theorem A.1. So what do I mean by this, right? So the Rham cohomology for any smooth stack even is canonically given by the crystalline cohomology of X relative to WK, so the derived mod P. In particular, you will be able to get the following short exact sequence, the HI crystalline mod P to HI the Rham to the P torsion of HI plus 1 of the crystalline. Right. So if you plug in, say, I being 1, right? Then Shubhodip told you that H1 Chris will be 0, so H1 the Rham is just P torsion of H2 Chris, which was the Dieudonné module. Okay, and then if you plug in I being 2, it tells you that H2 Chris mod P, which is Dieudonné module mod P, naturally sits inside H2 the Rham. So these two are the generators that we claimed in the Rham cohomology of BG. Okay. Right. So now, not only do we want to calculate the Rham cohomology, but we also want to calculate Christian cohomology. So let me write down this other theorem. And now, okay. Unfortunately, we haven't made full calculation when the prime is 2. So let me actually, very unfortunately, I have to say that the prime is not 2. But once you accept this assumption, then the Christian cohomology for BG, right, into WK also admits a rather simple description. It's given by the cohomology of this. I will write down this notation and then describe it. As graded WK as algebra. Well, okay. So actually, let me say that this is proof hasn't been fully written down. So careful, but we believe we can obtain something like this. So this L gamma is a derived version of divided power, and our input module is really the Dieudonné module of G sitting in cohomology degree 2, viewed as just as a complex, a perfect complex on WK. And for this, you can take its derived divided power algebra, and then you take its cohomology. And the result is whatever, it's some graded WK algebra together with some Frobenius action, and we're just claiming that there is an isomorphism as such. Okay, so maybe now I need to tell you how we can make some calculations like this, right?
So do you have information on the complex itself? Chris.
Right, so I was about to describe that, actually. Good question. But before, is there any question?
Also, if you're just interested in the group structure of cohomologies, it's actually P equal to 2 also works. It's on the multiplication and Frobenius.
Yes. Okay, thank you. Right, so yeah, let's say this is true as for P being 2, but only as I guess as kind of as WKF.
WK. I think F also is.
Oh, also okay. Right. I believe him as WK modules. So okay, graded WK modules.
I don't think we have counterexample.
We expect this statement to be we expect this statement to be true if you include Frobenius action as well, right?
But not as algebra.
No. I thought no, but it's okay.
You know what? This is not the best time to. Thanks. Right. Okay, but let's say that this is 99% true and this is 90% true, and not sure what happens if you generalize further. Right.
Wait, stupid question. So back there, is it true that such a G also lives all the way to WK?
Good question. I don't know. Yeah, I guess I just don't know. I also cannot immediately think of any counterexample. Yeah. Right. Yeah. Oh, but maybe I forgot to say this, but just to make sure we're on the same page. So I wrote down these 3 examples, and they are not counterexamples to the theorem. Namely, Z mod P and mu P does lift all the way to WK, and alpha P cannot be lifted to W2. Yeah, even as a group scheme itself, because of some result by Dieudonné that says if you can lift it, then it's automatically commutative. Yeah. Okay. Right. Okay. So maybe right now it's time to tell you. Right. So what are the general structure on cohomology of BG that we're utilizing to deduce these results? So the last theorem is saying that so this is kind of describing this complex or even somehow as an algebra. So the structure of R gamma BG, which again I deliberately didn't specify the cohomology theory, and it turns out that it's a very general statement or a very general phenomenon. So basically, what we figure out is that there is always a functorial multiplicative. Okay. Natural number indexed. Okay, so increasing, exhaustive nutrition on this object on gamma BG for really any kind of reasonable cohomology theory you can think of. This is always true, and it's graded. And then if you look at this the induced graded algebra, then that you'll be just given by this derived divided power algebra. Right. Kind of. I need to explain the meaning of this Dieudonné module. So basically, what I'm claiming here is that given your favorite cohomology theory, as long as it's not too terrible, you can extract out of G some very natural module called DG, a module over your coefficient ring. And then if you put this module in degree 2 and look at this derived divided power algebra, that would be this graded algebra. Okay, so for instance, if you look at Kristine cohomology, then this is literally the Dieudonné module. And if you look at, say, structure shift cohomology, then you will get kind of Dieudonné module derived mod V, and so on and so forth. Does it make sense? Or if you take the Rham cohomology, then you will get Dieudonné module G derived mod P, because that's how the structure shift and that's how the different cohomology theories are related for this particular class of stacks.
So should I think of this as, like, is there a finer statement that BG itself can be somehow degenerated into something simple?
I'm not quite sure if I'm. So I will sketch the proof, but basically, so the way the proof works is basically you prove similar statement but for BA, for any abelian scheme A, and then you can sort of unfold this description to get the description of cohomology of BG. So it's kind of from a kind of unfolding, unwinding process. Next question.
I'm just wondering, is there any hope of making this sort of motivic?
You will have to teach me what that means first.
And is the general definition of DG just like R1 of whatever filtration?
Yeah, you could define this way, or rather, you will say, okay, maybe locally. Imagine your G can be embedded in some abelian scheme. Then you can take the quotient, and then you take H1 in your favor in this favorite cohomology theory. And if it's reasonable, then the whole cohomology of A would be exterior algebra in H1, and then you take basically you take the complex given by H1 of the abelian schemes. And first of all, that will be independent of the choice and so on and so forth, right?
So the theorem also works for abelian schemes.
Yes, except there it's the Pastnikov filtration, right? So we're just unwinding kind of.
Is there any hope of having like a general statement for all commutative proof schemes?
Not just the finite ones. I'm not sure.
I think GA is somehow that example.
Yeah, I worry about GA.
I mean, for GM, it also works. Like the reason.
Right. So this works, yes, okay. So this also works if you replace G by GM and then also by a abelian scheme. Yeah. But let's first discuss something quite simple. So I wanna convince you that basically this theorem alone already implies our calculation of the Rham cohomology in a straightforward way. Yes.
So there's also a whole algebra structure from algebra, right? So is this isomorphism compatible?
It's an isomorphism of infinity for algebras.
Co-algebras.
Co-algebra.
Oh, okay.
If you only remember co-algebra structure. Thanks. Right.
Algebra isomorphism.
Yeah, but cohomology.
Yes. So let me quickly sketch to you how this can easily deduce our calculation of this Rham cohomology without going through the Hodge to Rham spatial sequence at all. So you can just take this statement, and then what you're gonna see is that basically the graded algebra on this. So you start with this filtration. Let's say your input cohomology theory is the Rham cohomology, then you will get increasing cohomology, then you do derive mod P, and you will get this kind of filtration mod P, and then the graded algebra on this Rham cohomology of BG is now just calculated by sort of derived divided power algebra of the actual Dieudonné module derived mod P. So it's a complex living over a field. Therefore, quite canonically, you can write it like this. So now the notation is terrible. So okay, so this P means I'm taking the P torsion of this module, and then this -1 means homological shift. Okay. And then also a part which is BG mod P, and then sitting homology degree 2. So this kind of polynomial construction, it will always turn direct sum into tensor. So we're just getting kind of divided power of this thing here, and then tensor over K with now gamma star K of this thing here. All right. And then it's just a result by I think already found in resist physics that if you do derived divided power of some kind of free module in degree 1, then it becomes exterior algebra. And similarly for here, you will turn degree 2 derived divided power of some free module in degree 2 will be turned into kind of symmetric algebra. So what we learned from Lucy, this declarge says that what you're gonna get is just the exterior algebra K BG P torsion minus star tensor K with symmetric algebra K of BG P okay minus P star. Okay. So you get some, a priori you'll get some result like this. And then it's not far from deducing the actual statement from this statement. So let's recall, what are we getting here? We're saying that on the Rham cohomology of BG, there is some very natural filtration whose graded pieces looks almost as what you want, except this cannot be literally true if I don't do this girl star, because this is not true when P is 2. Okay, so just have to be a little bit more careful to go through the spectral sequence associated with that filtration there. And then it's some algebra that you just have to do and then conclude our statement. All right. So let me just say that with absolute more work, we win.
More work includes computing the multiplicative structure on the cohomology.
Sorry?
More work includes additionally computing the multiplicative structure on the cohomology.
Right. So, So I think one part comes from really understanding what happens when P is 2, right? So for instance, from this description, you can already see that when I was, I erased it. When I was describing the algebra structure when P is 2, I said that the degree 1 class here, when I square, I will always land in this part. It's just because on this filtration, right? On this part, it's literally exterior algebra. So on GER, it's really exterior algebra. So this part will square only landing here. Yeah, and this kind of thing. All right. Okay, so in the last 5 minutes, let me just quickly tell you how you can prove this theorem C here. As I was explaining, the idea is this beautiful idea in BMS2 that there is a process called kind of unfolding, but I don't know how to abstract it out in this situation. And let me just tell you that first of all, by Reynolds theorem, we know that you can always embed G into some abelian scheme. Or in my case, for a field, I would just say abelian variety. Then you will get that G is a kernel of some P power degree isogeny. So in particular, you will get some. Okay, let's start with let's just think about this case of Krissing cohomology. Just from this sequence, you will get a natural arrow like the following: gamma crystalline BA prime WK map into R gamma crystalline of BG. And it just turns out that this is always an isomorphism for any reasonable I think here all you need to know is that basically the Christian cohomology, or as long as the cohomology theory for BA outputs symmetric algebra with generator in degree 2 given by kind of the Dieudonné module of A in your cohomology theory. And then the cohomology theory satisfies, say, smooth descent and satisfies Coulomb formula, then this thing will always be true. Okay. And and then one description of this filtration is just that you have Poisson-Cohen filtration on this guy, and on this guy. So you just take the push out, get a filtration on this, and its description is given like that. The only complaint you might have is that this is not functorial enough because this involves a choice of G embedded in A, right? So to make sure that this is really functorial, which could be useful for other applications, then you can just consider the category of all homomorphisms from G to some abelian scheme A, and I no longer require this to be a embedding. And it just so happens that you can use this result to show that if I look at the colimit parameterized by the opposite category of this C, then R gamma BA maps isomorphically to R gamma BG. And as I kind of alluded to, so on here you have this Poisson-Cohen filtration, and then take the colimit of the Poisson-Cohen filtration gives the same filtration there, which that's the job. Right, I should stop here.
But I think about how the lifting properties are related.
Yes. So the lifting comes from so the lifting the hint on proving lifting. Okay. Liftability. This is just because this cotangent complex of BG relative to K is given by a bunch of structure, right? A bunch of structure sheaf, drag sum, bunch of them shift by -1. So usually, right, when we study deformation theory, you have to worry about so we're looking at some obstruction class in, say, H2 of T. What that really means is somehow a degree 2 homomorphism from L to O. Even though it could happen that that arrow itself is non-zero, but induces 0 on cohomology, but that's no longer the case because of this. Therefore, all you need to know is that the obstruction map will induce 0 on cohomology. And turns out that this obstruction map is related to conjugate spatial sequence. It's one of the arrow in conjugate spatial sequence. And we can use that to deduce this kind of, to relate liftability literally to Hodge to the Rham degeneration. Yeah. Yes.
Does this filtration coincide with the even filtration? BG?
Right, so what does it mean? Well, that is a good question, but
I was just kind of confused because if I don't know, maybe I know nothing, but there they take the limit over map ring, and here you kind of map out of even rings.
right. So yes, so this is what we wondered.
I think that they're mapping out of even co-elder. So maybe if you, I don't know. But
It might have to dualize or something, because also their even filtration is decreasing, whereas ours is increasing. And
Great.
So here the colimit holds as a like, does it hold as filtered algebras or?
sorry.
Does the colimit equality, like the last thing you said, hold as filtered algebra?
Yes, because the filtration here is given by colimit of filtration here. So I'm first saying
way
that,
to define filtration.
yeah,
Okay.
but we're using this underlying isomorphism to define filtration.
Wait, sorry, can you come? You said something about G to A doesn't have to be injective. What was the relevance of that?
Oh, sorry. So here I'm really considering all homomorphism.
I guess I'm asking what does that flexibility buy you? Oh, I guess it allows you to consider the
That allows me to have functoriality, right? Because if I have some G to H, then H embedded in A doesn't induce G embedded in A. So this will behave better with respect to map of G's.
Other questions? Let's thanks for jumping again.